from the Indian Institute of Technology, Bhubaneswar. He received his PhD from the University of Groningen in Netherlands and his master's from IIT Bangalore. And his talk is titled Mechanics of Nanoporous and Microporous Metals. Sir, over to you, sir. Mangipudi from IIT Bhubaneswar. He received his PhD from University of Groningen and his master's from IIT Bangalore. Today he's going to talk to us about mechanics of nanoporous and microporous materials. Sir, over to you.
Okay, so you see my full screen?
Yes,
okay, so
yes, it is perfect. Yeah.
Yeah, it's fine. Yes.
Okay. Sorry for the trouble. First of all, let me thank all the organizers and for giving me this opportunity to present my work here. So today, what I will be talking about is the mechanics of porous materials mainly, and particularly I will be focusing on nanoporous materials in there for today. But a portion of it also, what I was will be talking about at the end is about in general, how do we deal with the cellular materials or porous materials, the mechanics of porous materials. So the outline of the talk will be like this. So initially, I will introduce what are these nanoporous metals. I'll give some description of their structure, why we are calling them porous and nano, and then give a little bit of a brief idea about how these are made. And then the main motivation where we started actually looking at this. I'll be talking about actuation in nanoporous metals. And here I'll first briefly discuss the phenomena and then how we attempted to model this phenomena. And then I'll move on to how the structure of cellular materials is important for us in this kind of applications. Why it is important and how can we actually try to take it into account? How do we quantify it? And what are the main aspects of this structure? And then finally, I'll try to show you that how we were able to capture it quantitatively. So this is the last portion where I'll be talking about portions which are generic to all cellular materials. Okay. Okay, so nanoporous metals are kind of porous metals, and the porosity or the length scale of the ligaments, what we call them, are the ligaments here. So they are on the nanoscale, so tens of nanometers, from a couple of nanometers to tens of nanometers. So here you can see an STM image of a nanoporous gold, which looks like a Swiss cheese, but a very, very porous one. And the gray areas are the ligaments. So these are continuous. So this whole structure is fully connected. So this is like a network, like our bread, you can imagine, sort of. And this is all one single connection, okay, one single material. So and you can, as you can see, so this is like 300 nanometers. So in this particular example, the ligament size is on the order of 30 nanometers, but we can even go down to 5 or 5 nanometers too. And if we want larger ones, we can do post processing of the as produced synthesized structures and can increase the length scale by coarsening through annealing. So this is how the three-dimensional structure of the same would look like. So this is an fib nanotomographic reconstruction shown here. And imagine that this all of it is actually a single crystal. So in a single crystal, what I mean is, so the pores are, you can imagine them to be, the pores to be carved out of a single crystal material. Okay. So there are no grain boundaries in this. So the crystallographic orientation of all these struts that you see is actually the same. But the orientation of the struts is going to change, as you can see. You can produce them through various methods like de-alloying or block polymer template techniques. The most popular one or widely used one is the pre-corrosion technique. So that's because it is the simplest one. And through this method, we can produce not just nanoporous gold that is shown here, but we can also produce nanoporous platinum, copper, and other metals too. Even some nanoporous steels were also produced. So why? So how is this structure made? So it's the de-alloying technique, which I'm going to describe, which is the easiest one among the various processes available synthesis methods. Here you simply start with an alloy. Okay, so for the case of nanoporous gold, we start with gold-silver alloy with some desired volume fraction or atomic fraction of gold and silver, and you just put this alloy into a corrosive medium, for example, like nitric acid or picric acid. So in this alloy, we have actually two elements. One is gold and silver. So the silver is less nobler than gold. So it gets first attacked by the acid and it gets dissolved. It is corroded into the aqueous medium. And when that happens, so that happens around a region. Okay, so at the surface, there is a region of attack, very, very thin, of course, but this corrosion actually progresses into the metal. And as this is happening, so once the silver atoms are dissolved into the aqueous medium, the leftover gold atoms, which are nobler than the silver, so they will start to group together, so through surface diffusion, and then slowly build up these mounds. And these mounds, as the attack continues, so they get bigger and bigger, and then they may also undercut. So once they are undercut, so you will start to have this very complex three-dimensional bicontinuous network of pores and the metallic ligaments. So this process, actual process, is believed to be a spinodal decomposition, but which is quite not the same as solid state one. But it is still, the exact mechanism is still argued upon. But finally, what we get is a very interesting bicontinuous porous structure. And we can also produce other metals, porous metals. For example, here we have produced nanoporous copper starting from an aluminum copper alloy. And in this case, there are two phases, alpha aluminum and Al2Cu. So the aluminum gets dissolved when we put it in an 1 molar sodium hydroxide solution. So the aluminum atoms will be dissolved and copper will be left over, because copper is more nobler than aluminum in the electrochemical series. And the resulting structure is something that looks like here. Okay, so all the aluminum is dissolved into it, and also the aluminum from this aluminum copper is also dissolved. And therefore, in these places, the light gray places which are aluminum to copper, So the aluminum is gone, so copper is left over, and we have this porous structure. So what we get is essentially a hierarchical porous structure in this case. And a blown up view of this is shown here. So these ligament sizes are at the nanoscale. So why are these materials interesting? So as you can guess, it has quite a bit of open porous structure. Okay, so that porosity, which is at the nanoscale, is one thing that is very, very important for various processes like catalysis and other phenomena which actually depend upon the large surface area. Okay, so this nanoscale gives us a large surface area. And in addition to that, the synthesis process allows us to tune the length scale over a very wide range. Remember, I mentioned a little while ago that we can tune the ligament sizes anywhere between submicron to a couple of nanometers, 3-5 nanometers. Okay, so that gives us a very huge, a degree of freedom there. So we can turn the knobs over a wide range, and then we can, because of that, we can tune the properties which are dependent upon the resulting surface area and the phenomena. So you can imagine several applications for such materials like fuel cells, anodes for fuel cells, and also maybe in batteries as well. And sensors, because of the surface area, the catalysis or chemical reactions can be exploited. And those can be used as sensors, and also electrochemical actuators. We will discuss about it in a while. Supercapacitors and many more. You can imagine. Okay, so this is not yet into an engineering application yet, but it has got quite a bit of potential for that. So what I will be focusing in the next few slides is about the actuation behavior. Actuation behavior of these nanoporous metals through electrochemical means. So what is this essentially? So this is a nice experiment done a while ago. So in this experiment, these Weissmullers and co-workers, they have taken a nanoporous gold leaf, which is actually not entirely porous. So the de-alloying was done partially in this thin film. So there is a slight backbone of the alloy, solid alloy that is left over here. And then there is a huge portion of porous material on top of it. Okay, so that gives some mechanical integrity, better mechanical integrity. So a similar leaf is also placed on the other side, and they have applied a voltage potential difference across the two. And it was kept in an electrolyte. So what happened is that what they have observed that after application of the voltage, these leaves have started to bend. They have deformed, as is shown here. So the mechanism that they proposed initially is that when we apply a potential difference here, when the metal is, even though the metal is a noble metal, okay, so immediately a double layer is formed because of the potential difference between the electrode and the metallic surface. Okay, so and that metal layer now induces a charge here, a negative charge on the surface of the metal. And because now the charge here is more, and that charge is believed to induce some stresses on the surfaces, and those are believed to cause the deformation. And as you can see here, so these are the experiments of repeated potential application. So the potential was actually varied between almost 0 to a higher value, and this behavior is quite reversible and is reproducible. So which means that it stays very long. So it's all elastic deformation. So here you can see the potential is varied, okay, all between this range minus 0.2 to 1 almost. And then the black line indicates the change in length of these nanoporous structures. Okay. So then they have calculated the charge that you could expect over the surface, and then they saw that the potential and the charge are very linearly related. Okay, so in other words, we can also relate the strain in the material with the applied charge on it. So this is what gives us a behavior called the charge-induced actuation. So which they term it as a charge-induced actuation. So we put charge on the surface in the material, inject charge into the material, and that causes the deformation. So now you can imagine various applications for that. Okay, so as actuators, maybe in very small scale applications like lab on chip and so on. And if you can very intelligently engineer this strain, okay, and the structure, we would be able to propel some fluids, for example, or you can use it as chemical sensors in certain places. So a lot of applications can be now imagined. Okay, so let me skip this part. So basically, I'll very quickly go through this. So this is here. So they carried out this chemical reaction on the surface of this nanoporous gold and measured the actuation response here. So what happens is that once the ozone is passed through the porous material, the ozone decomposes and leaves an atomic adsorbed oxygen atom on the surface. And when you pass carbon monoxide through it, and that carbon monoxide reacts with the adsorbed oxygen, and then the oxygen would leave, leaving behind a free virgin gold surface. And this process is now actually putting charge when the atom, oxygen atom is getting adsorbed and then desorbed or being removed. So it changes the charge on the surface. As a result of that, they have also seen a reversible behavior here. Okay, of course, they have to use some nitrogen purging periods in between so that you can completely remove all the adsorbed oxygen. But you can see that this using chemical reactions can also be used either for sensing applications or using them as a means of actuation in small structures. So now so this is the charge-induced actuation behavior, which was very interesting, and these are sometimes termed as metallic muzzles with a great enthusiasm. But how and experimentally it is proven. So it was discovered first experimentally. So how can we exploit this phenomena, and then can try to design some useful engineering components. And if we want to do that, so we thought like, let's see how we can model it. And what the basic phenomena, as I have just explained, is actually the charge that is induced on the surface and the stresses that are developing because of that. So what exactly is going there is, so this behavior actually dies down, or the response dies down as we increase the size of these ligaments. Why is that? Because as you can see here, so this is a schematic shown here. So as you decrease the particle size, so this is for a spherical particle here, you can see that the fraction of surface atoms increases, whereas the fraction of bulk atoms decreases. So if we have a larger sizes, then the atoms that are participating in the surface would be very, very less compared to the bulk. And they would only become significant if we go down to smaller sizes. So therefore, the nanoscale structure is important and responsible for having this phenomena here. So what exactly is happening here? So if we have, let's say, a bulk of this material, we know that there are these electrons that are valence electrons that are given by these metallic kernels, and of course it's in metallic bonding, these bonding is diffused, but nevertheless because of the coordination, you can imagine that, okay, so there is a more likelihood of finding some electrons nearby these atoms in certain directions because of the directionality. Okay, so this take it as a schematic thing. So there is a coordination now here. But if we cut the bulk over here and remove the upper portion, okay, then we are left with the surface atoms. So these atoms now become surface atoms. And Until then, the valence electrons of this are being now shared by the other atoms which are next to the neighbors, and now they are gone. So because of that, what you could imagine is that there is an excess electronic charge, excess or depletion, depending on the type of the surface, the crystal structure of the surface. So that now what happens is that that has to get redistributed near the surface. And because of that, because now the coordination here is different, so the electronic density is also different there. Okay, so this basic idea has been proven by DFT calculations here. So here you can see that I guess this is a copper surface, 100 surface. So if you look at the electron density, so the electron density at the first layer is quite high, and then it's slightly higher at the second layer, and then after that, okay, so it's much less than this. Okay, so we have a higher electron charge distribution near the surface. And now you can think that, okay, so the charge, more is the charge, okay, so then the bonding between the atoms would be greater, right? So the the energy, the energy landscape in which the atoms are sitting is now not anymore the same. So the bonding characteristics are also going to change, and those that will be very different compared to the bulk atom, and that induces stresses in the surface. So that could be either tension or compression, depending on whether we have excess or depletion of this charge near the surface. And those stresses can be very, very large if you are looking at a small structure. Okay, so if the length scale of these ligaments is small, then the stresses can go as high as gigapascal. Okay, so here we have compression going up to a couple of gigapascals, and also in the tensile regions here. Okay, so I missed the color bar here, but the stresses here are actually more than a few gigapascal, 4 to 8, I guess, for this length scale. So it's very huge. So what is happening, as I mentioned, so the atoms are actually sitting in a different energetic environment as you come from the bulk and close to the surface. Okay, so there is a difference in that. So that excess energy you can attribute to that to the surface, and that's the origin of the surface energy what we have. And if you look at that surface energy, okay, so if you expand that surface energy, we know that, okay, this is a function of the strain of the atoms nearby, okay, so near the surface. If you expand it, then in a Taylor series, so this is what we will see. Okay, so the strain and surface energy expanded as a function of the surface strains. Okay, then we can identify that in the Taylor series expansion there is a surface stress. Okay, initially. So, and in addition to that, we can also see a second order tensor coming up over here, which we can relate it to the elastic tensor. So this is what gives rise to the different elastic behavior of the surfaces, and you can connect it with the atomic arrangement of the surface, because the atomic arrangement is different, so naturally you can expect a different elastic properties over there. But remember, it's not really a big volume over there. It's typically 1 or 2 atomic layers thick only. So it's not truly a bulk or volume type of elastic tensor, but it's a surface elastic constant. It's for a membrane. Okay, so there is a theory, surface elasticity. I will not go into the details of it, but the theory is conceived this way, that if you have a bulk, okay, which can be modeled using the regular elasticity, okay, and then imagine that volume is now attached with a surface with a mathematically zero thickness. Okay, and that surface now behaves according to the surface energy that you can compute based on the atomic coordination near the surface. So neglecting higher order terms, now you have the initial surface stresses coming from there. So if you take the derivative of the energy with respect to the strain, then you can get this. and then based on the surface strains, you can also get the surface stresses, and the surface stresses can now be related to the tractions that connect the bulk and the membrane. So this is the connection that establishes the physical connection between the bulk and the surface with mathematically zero thickness. Okay, and of course there is another one. So this is the in-plane stresses in the surface, and this is the out-of-plane forces that balance the bulk with the bent surface. So that's where this is the curvature of the surface. Okay, so I just wanted to give you the gist of it. Due to the in the interest of time, I won't go into the details of it, but remember that this I would be coming back to it in order to make a connection later. So now how do we want to model it? So we want to keep the same kind of picture in mind, but in order to implement it in a numerical method, okay, treating this is going to be a very, very difficult thing. And remember, in this case, so the equations that what we have got are actually involving a lot of simplifications, which otherwise which are not really acceptable when you talk about crystalline nature of the surfaces. Okay, so what we thought of is that let's assume that, okay, so all these surfaces are kind of anisotropic, and then we give a fixed elastic tensors and a fixed initial surface stresses. Okay, and in our initial attempts, we also neglected the surface elasticity tensor as well. So what we imagined is that let us consider the nanoporous structure. Okay, so here we cannot use the atomic description because it's computationally impossible to deal with, and therefore when we wanted to handle large volumes, the only way is that to go for a continuum approach. And in the continuum approach, we will treat this volume, nanoporous gold volume, as a bulk material attached with a membrane. So the core elements here, so when you discretize it in FEM, so that we have a core, solid core that goes as a regular continuum, and then we attach to it a surface which will be meshed with shell elements. And to the surface, then we want to put some strain. So that's the easiest way you can implement it. We chose to work with abacus, and the easiest way there is to put some thermal strains, eigenstrains over there. So we wanted to put the strains which would be a function of the applied charge. So that was the basic idea here. So that's the easiest implementation. So this is the scale bridging that one needs to. So in order to do the scale bridging, so we need to get this parameter. Okay, so how much strain do I get for a surface for a given amount of charge that I'm putting it there? So this parameter we will now try to get it from the atomistic simulations. Okay. So when in order to do the atomistic simulations, now we have to modify the existing available potentials so that they can incorporate our desired level of external charges. If you look at the regular EAM potentials, so in an MD setup, what you have here is this is the potential energy. The important part for us is the electron density. So the metallic kernels are assumed to be embedded in a electron C, kind of C. Okay, so with a given electronic charge distribution. So this is the rho. Okay, so and of course the charge distribution comes, this electronic charge distribution density comes from contributions from individual atoms that we have. So this is the regular setup. So what we have to do is that now we have to modify this portion so that we can inject some charge onto it. So we started with already a modified potential, which is called surface EAM potential, so SEAM, which actually takes into account that when you have a surface, there is a problem of coordination. Okay, so reduced coordination, and that reduced coordination was taken into account in this case. So that's a natural redistribution of the electronic charge. So that was the SEM potential, surface modified EM potential, and that contains this F1 and F2 terms. So I'm not going to the details of those. Now to that, we had to inject an additional charge at the surface. Okay, so and then we have added an additional term which would modify the electron density near the surface. And here is our charge. Okay, and of course there are some parameters, and we need to calibrate them, and that's we do it through some simple taking simple geometries. We try to do the calibration, so which that I'm skipping here. So now you can imagine, you should believe me that okay, we are able to do it faithfully enough. So when you do that, you can see here. So for for various induced charge densities on the surfaces, we can get actuation strains for various crystallographic surfaces. You do several simulations and you can get it. Okay, so most of these simulations are actually done by my colleague. Okay, so he was a PhD student in our former group. So Shiva. So these nanowire simulations were actually done by him. So now you can see here that the interesting behavior and lucky for us is that the charge versus strain behavior is pretty linear for various surfaces and also for various sizes. So there is no nonlinearity that has been observed. So that's a good thing for us. Makes life easier. Okay, so now you can take the slope of that, and then you can look at what is the strain and the rate of strain for a given amount of charge induced onto the surface. And you can now do the same thing for various surfaces, and you have that behavior established. So now we have this charge versus strain behavior, how to relate this parameter. Okay, so while doing it, what I have actually skipped here is that when we do these simulations, we cannot directly measure the strain. So because if you take finite size samples, that gives us a trouble. So what we do is that we take nanowires with periodicity and then fix the strain. So the strain is fixed over there. And then for a given charge, then we will measure the stresses through these simulations. And from the stresses, we take the elastic stiffness tensors, okay, from here through some other simulation. So once those elastic stiffness tensors are tensor components are known, then we can invert the stresses and then get the strain versus charge behavior for it. So once we have established this, then we went on to look at the real structures. Initially, we looked at gyroids, which are lattice materials, in the sense they are periodic and regular porous structures, and looked at how the strain for a given amount of charge, here kept the charge constant, it varies as a function of the length scale of this and also as a function of the volume fraction. So this is the volume fraction here. Not the rho star indicates the volume fraction of the material here. Okay, and then we also looked at more random structures over here. Okay, these random structures are the nanoporous gold, and there also we repeated the similar experiments, and we saw that the strain here, if you now try to see what is the behavior, very surprisingly, the actuation behavior of these gyroids and the random nanoporous structures both are coinciding with each other. And if you do structural analysis, for example, so here I am showing how the curvature of these ligaments is varying from point to point at different points. So this is a probability distribution of the curvature. So maximum principal curvature and minimal principal curvature at a given point on a surface. So if you look at it, the gyroid and the spinoidal structures are extremely different candidates. But despite of that, what we see is that the actuation behavior is exactly the same, and the connectivity is also very different. So that led to the question of how the structure is not playing a role in this, and how we know that the mechanical
Sorry, we seem to have lost Professor Mangipudi.
Yeah.
Just wait for a minute.
Of them, and also various other
Kodanda, we
factors.
briefly lost you on the previous slide. Can you?
Okay, where here?
No, previous.
Yeah, here, yeah.
Here.
Okay, so basically here, what the conclusion that we can arrive at is, although the the real nanoporous structures and the gyroid are very different in terms of their surface curvature behaviors and connectivity, we saw the similar behavior. So the question came how the mechanical properties are then related to the internal structure. So we carried out a series of investigations, long investigations, but I'll go to the final gist of that.
Professor Kodanda, may I request 2 minutes? Would it be enough to wrap up?
Yes, this is the final slide.
Yeah, thank you, sir.
So here then what you can see here is that we have done the similar exercise of trying to relate, quantitatively get the connectivity information in a parameter called genus, which is a measure of the connectedness in the structures. We took large variety of structures over a wide range, and we see that here that the mechanical properties, so these are the factors that relate the relative density to the relative modulus and relative strength, and they are pretty much quietly related. So with this, okay, so once that relationship is known, we can establish the connection between the quantitative connection between the internal structure and the mechanical properties. Okay, so I know that in the last part, so there is a disconnection here due to the lack of time, but if you're interested, please write to me. We can discuss a little bit more on that. And with that, I conclude here. Thank you very much for your attention.
Thank you, Professor Mangipudi. Thank you very much for that wonderful talk. We will now open the floor for questions. Ladies and gentlemen.
Parag, can I ask a question?
Yes, certainly, please.
Yeah. Hey, Kodanda, very interesting talk. I just have one question. So you have shown this in the manufacturing process, this initial gold pellet, right? Yeah. So you say, is that also supposed to be a single crystal pellet or?
No. So that is slightly quite big. The samples are quite big actually. So this is like this. So this is a very large polycrystalline sample on the millimeter scale. Okay. So when the de-alloying happens, it removes all the less noble atoms from these individual grains. So this whole grain, which will have this structure there inside it. So in a larger sample, we do have a polycrystalline nanoporous structure, and individual grains will be having exactly. So this is before and after de-alloying. This is an EBSD map which shows the crystallographic orientations in these regions. So here we can see that the orientation has not changed; it has remained. So it is as if it's a very interesting behavior. So it is as if we are simply removing the alumina. In this case, it is the silver atoms out of the crystalline lattice.
All right. Yeah. Thank you.
Yeah. Thank you.
So are there further questions?
Okay, so there was a question which is asking, so what is the software used for these simulations? So the MD simulations were done in labs. So the potential was modified, and the modified potential was used as an EM potential, MEM potential. And then the rest of the simulations were done in labs. And the continuum simulations, those were done in Abacus. So the charge, so from a given, for a given charge, so we know how much strain that needs to be applied, and that strain was applied in terms of a thermal strain, and which is applied to the shell elements. So it basically becomes a surface loading. You could also simply do a surface loading and use an user subroutine, but we thought that's the easiest way to attach it to a shell element and then do it.
Okay, I think, yeah, so we can thank Professor Mangipudi once again for a wonderful talk, very interesting material. Thank you, sir. Thank you very much.
Yeah, thank you all. Thank you very much, too.
Yeah. Thank you, Parag, for chairing this session. And I also would like to thank all the speakers over the last 3 or 4 days, including this Phoenix workshop, who helped us deliver a very interesting workshop with exciting and engaging talks. And also the participants who have been very active in asking questions. And we hope to meet again through such workshops in the future. Yeah, I think with that, Anand, can we close the workshop? Yeah, I think Anand is not there. So anyway, so thank you very much, Kodanda, and thank you all for joining us. Bye.
Thank you. Thank you. Bye-bye.